I'm not going to say we saved the best till last, because that's probably not doing justice for our other speakers as well. But I'm really interested in this session, and Dave Farley is a great speaker. So vibe coding, is this the best we can do? I think this is going to be an interesting look at the processes and the practices we do today with vibe coding, what needs to go forward into our new practices. This is the last session of the day before the party, so afterwards I'll let you know a little bit more about what the party's doing. But in the meantime, please make sure you're still doing your ratings and things like that on the app. But without further ado, please give it up for Dave Farley. Great session.
Thank you. Thank you. I'm the last speaker between you and beer, so I'll try not to go on too long. I'm interested in the things that seem durable. And that may seem odd when we're talking about such a disruptive change as we are talking about when we're talking about the adoption of AI for programming. But I think there's quite a lot of things that are durable. There's a lot of behaviours that have stood the test of time and seem to continue to be important. And I'm not the only person that's been saying that today. If you've been listening carefully, there's been people saying very similar things as we go through. I'd like to look at maybe some of the reasons why this matters and question some of the things that we may otherwise think about the new world of agentic programming. I think one of the things that we can certainly say, though, is that whatever does come next, it's going to be different. This is a huge change. This is a sea change in the way that our industry, and probably our industry is just a forerunner, how our world is going to work. So what does this really mean? What does this mean in terms of the impact on people like us who are involved in the production of software at the moment, and I suppose to some degree the pathfinders for everybody else in the world as they start to adapt to some of these things? I think a starting point, if you'll forgive me for being slightly provocative, some of the differences that we talk about are kind of just dumb. So I would argue that vibe coding, programming with natural languages, while having a place, are also kind of bad ideas. And I want to talk a little bit about what I mean by that, and we'll get into it. I think sacking all junior developers, AIs will write all the code, we don't need no programmers. Some of these are kind of right, some of them are probably true, and some of these are a terrible idea. I think AI-generated tests, also a terrible idea. So I'd like to explore all of these things in a bit more detail, and there's quite a lot of nuance in this, because there are aspects of these where they're all true. But let's talk about it. So first of all, I'm a old school card-carrying test-driven developer. So let's start with tests, because that's where you're supposed to start. What's a test for? Is it to prove success? Not really. Is it to find our mistakes? Well, kind of, but not really. Is it to challenge my genius as a programmer? Certainly not. It's not. Those are not really what tests are for. They're not what make tests useful. I would argue that what tests are for us, they're our form of measurement. They're our equivalent of a carpenter having a tape measure in his pocket that he can measure things with. We use tests to figure out that we're doing the right things. We use tests to figure out that when we've done them, they continue to be the right things. They're measurements to see if we've achieved our goals. But for that, we've got to define what our goals are. And we can't infer the goals from the solution, because the solution can always be wrong. So anybody that's selling you free AI testing that will come in and look at your existing system and test it, that might have some value, but it's not the same value as proper testing that we need as part of a development process. It's a different thing. And the reason for that is fairly obviously. If I write a function, something like this, calculate task, and I'm going to return 50 times the amount that I put in, that's a very bad place to live if that's what your tax looks like. But if that's my starting point, the only thing that an agentic AI or any other kind of AI can do is look at that and say, okay, here's my test. It's just going to reinforce the wrongness that I wrote into that function. All that a test can do at that point, because the only input it's got is the test, is the working code, is verify that the working code does what the working code does. That has its uses. That's very good if you want to refactor the code, do behavior preserving change and not break anything. But it's rubbish if you want to develop a new system and verify that this new system continues to do or does the right things, because now it's proving that it does the wrong thing, because that's where we started from. So that's not giving us an ability to define what we really wanted. AI-generated tests, if the code is the only input, we can only verify that the code remains the same. We can't infer the goals from the solution, because the solution can always be wrong. So they're mostly a dumb idea. They have a place, but mostly a dumb idea. They tend to be a cop-out for people who can't be bothered to state their goals. And I think that's a problem, because specifying the goals is kind of what our job is. It's kind of what we're here to do as software developers. My next question, what's a program for? To define a sequence of instructions. Well, not really. That's not the goal. It might be what it is, but to encode algorithms, that's not the goal, again, of a program. That's not what we do it for. That's not the value that it brings. To implement our brilliant design, again, that's some of the self-fulfillment that I, as a programmer, might get from it, but that's not the goal. That's not the goal. That's not the reason that people pay me to do it. So the commercial pressure is none of those things. That's not really what it's for, as much as we might like to think of it in that way as programmers. Programming languages, I would argue, have three goals as tools. So first, they are tools that have been designed to help us to organize our thinking about a problem. They allow us to explore the surface area of a problem and kind of understand it in more detail, in more depth. And they're designed to work that way. Programming languages aren't difficult because we wanted to be obscure and abstruse. We wanted tools that would help us to explore the problems in this kind of way. They're designed to help us to do that. They're also a means of communicating our understanding with other programmers, other humans. So they are a communication tool between us, so we can work as part of a team and understand what we are in some technical detail, exploring the depth and the breadth and the complexity of the problem that we're trying to solve and the solution that we've come up with, encoded as a program in a programming language. And ultimately, they're there to tell a computer what to do. But that's kind of the last part, because assembly language instructions inform a computer what to do perfectly well. And not many of us spend our time writing programs in assembly language. There are also three techniques that are embodied in programming languages that I think are important for us to think about and to remember when we're talking about programming as a discipline. The first is we have a simple, consistent grammar. It allows us to express our ideas in a concrete, specific, precise way, precise enough to be executable by a computer. They are an unambiguous expression of our intent in that respect. And that this matters. And they're repeatable and deterministic in terms of execution. And this matters a lot too. If we write something in the programming language of our choice and run it twice, given the same inputs, we're going to get the same result every time. That's important. It means that we can reason about it. It means that we can test it. It means that we can understand what it means. And we can design systems that are more or less repeatable in that sense, but the tools themselves are repeatable. How does natural language measure up to that? Because natural language, somebody said today, I think they quoted Andrei Karpathy saying that the programming language of the future is English. I don't like that idea very much for the reasons that I'm talking about. It's not precise enough, it's too vague. Natural language helps us, how does that measure up? Helps us to organise our thinking about a problem. Well, it's too vague, really. Natural language is open to misinterpretation. If anybody's been around, I can't really see you very well, but if you've got a grey beard like mine, or you've been around enough, I bet that you've been in a situation where somebody's coming down from on high and given a very vague instruction to a bunch of programmers, gone away, and then been really disappointed in the result because they didn't tell us in enough detail. That's really common. It's really easy to misinterpret what the goal really is. Natural language is always open to interpretation. Time flies like an arrow. These are some time flies liking arrows. Vibe coding alone is simply not good enough. If we're just chatting with the computer to express our needs, that's not enough. We need tools that allow us to be more precise than that, to be more specific than that, to be better prompts of what it is that we want to achieve. That doesn't mean that we need to look at all the code and are only allowed to do this in a programming language. I'm in the category of it's been a long time now since I've written any code by hand because my AI agent writes all the code. But I've been more precise than just natural language in some respects in specifying what I want from it. I'm able to get what I want from it by using a precise, prescripted version of natural language in order to be able to prompt it. And that's what I'm really talking about here. So, does it communicate our understanding with other humans? It's a bit too ambiguous to do that very well, because as we all know. Does it tell a computer what we want it to do? It's too imprecise for that, so it's very easy, unless what we're telling it is something very obvious, like asking our AI assistant to implement FizzBuzz for us. It might do that in a repeated way, but otherwise it's probably not. It's going to be a little bit different and give us something a little bit different every time. Certainly in the earlier versions of AI coding assistants, we've all seen that, where we've asked our system to build something, you ask it the same thing again and you get something very different. That's certainly happened to me a few times. So we've got these, what about these three techniques that we have? Simple, consistent, formal grammar. Does natural language give us that? No, it's complex and inconsistent. Unambiguous expression of intent. No, it's ambiguous and vague. Repeatable deterministic execution. Not repeatable, not deterministic, not version controllable as a result. If we version control the language that we prompted our AI with, that's not enough to get back to the same result again on its own. So programming with AI presents three important problems for us to replace traditional programming. So how do we specify what we want with precision? That's problem one. Problem two is how do we confirm that we got what we wanted? This is the verification problem. And problem three is that we don't work in the same way as the machines. They don't work in the same way as us, either way which you look at that. The way that we do things is that we tend to deal with problems with the limits of our own context window, so what will fit inside our heads at a time. We might have a picture of what it is that we want to build, but then small change by small change, the way that we deal with it is that we do it incrementally. We do a small piece of work, we evaluate that piece of work, and then we move on to the next small piece of work. I would argue that high quality system development in software is always an incremental process of learning and discovery. We are always exploring the problem space and trying to understand it over time, bit by bit by bit. I'd go further than that. I would say that's all engineering. All engineering is an act of incrementally improving on what we know about the problem and in dealing with the new things that we learn as we do that over time. And that's a hard part of software development, a hard part of engineering in general. And then we've got to verify that we got what we wanted and it does all of the things that we need in a repeatable, reliable way. And that's a hard part of software development as well. And what have we done? We sped up the coding bit. That was the easy part of software development, which is good. It's great. It does accelerate us. But it also moves the bottleneck. If you've ever read The Goal, the theory of constraints, that's what we've done. We've just moved the bottleneck to somewhere else. And actually, we probably haven't moved the bottleneck because the bottleneck was nearly always about verification and release and figuring out what we really wanted rather than the encoding of it if we were any good as delivery agents. So an AI works differently. An AI works, it kind of builds this context, this picture, and then it goes bang, and it makes a huge change. Probably until recently, you kind of rewrite the whole system every time. And there's nothing really to stop it while it's building your stock control system to write Space Invaders instead, if we haven't told it not to, if we haven't defined what our goals are and are in a position where we're able to evaluate it. Now, part of the problem here is that a lot of people that talk about using AIs and AI agents to help with coding are often talking from a perspective of building small, simple systems. I don't know about all of you, but those aren't the sorts of systems that I generally build professionally. They're certainly how I've played with the AIs. I've written Space Invaders with an AI agent, and I've done simple things like that. All those nice, straightforward things. But my professional building of software has been for bigger, more complicated systems than that. And that's not good enough. Just being able to check them manually to see if they're okay is not even close to being good enough to verify that we get what we wanted. So, if the AI is making huge steps and changing things in one big change at a time, and we're not able to verify that we got what we wanted effectively, how do we learn? How do we refine our understanding? How do we reliably update our solution to improve it? And how do we regenerate it if it's regenerating it from scratch every time? It can't. It's not really helping us to learn and adapt and figure out where we are and figure out what we need to do next. It's a problem. The last two problems, problems 2 and 3, mean that we're losing our ability to work incrementally. And that is fundamental to building complex systems of any kind, but certainly complex software systems. It's this process of learning and discovery. So how do we keep our ability to learn, discover, and incrementally add to our systems as we go? We have to have a means that can keep up with the rate at which we can produce software. I spoke to somebody not very long ago who's engaged wholeheartedly in the adoption of agentic programming using multiple agents to build systems. He's writing a game. He reckons he writes 12,000 lines of code per day. No human being can review 12,000 lines of code per day. No human being can manually test the output of 12,000 lines a day behaviourally to figure out whether it's doing the right things. We've got to find ways of speeding up the rate of verification and assurance to tell whether we got what we wanted to keep up with that speed of generation of code. It's the only thing that makes sense, it seems to me, if we're not to suffer from the theory of constraints problem. How do we confirm then that we always get what we want? So first we've got to specify what we want, clearly reproduce in a reproducible manner, and then we've got to be able to verify repeatably that we still have it after every change. If you're familiar with my work, with continuous delivery and so on, that might sound familiar. It's because it is. It's the same that we've been doing when we're talking about practicing continuous delivery. It's table stakes. We have to have this fast cycle of verifying that we got what we want. So, how should programming change to keep up with all of this? So, problem one, specifying what we want with precision. In the past, the way that we did this was that a program was a precise solution encoded as algorithms. Weirdly, we kind of lost what the problem was. It's kind of implicit in our solution, but we'd keep that in our heads and we'd build a solution, and that would be our definition that we'd work to. But the solution itself was implicit. So in my example, this is a routing algorithm. So I'd like to find my way home is the outcome that I'm trying to achieve here. In the future, a program will be a precise description of what it is that we want, I think. Encoded as specifications, translated into executable instructions by the AI that will verify that we got what we wanted. And what we want now is explicitly part of, if you like, the program. So the program moves away from being solution-focused to being a more accurate description of the problem that we're trying to solve. I'm describing a form of spec-driven development, but the specification takes the form of executable specifications, tests if you like, that both specify what we want and also verify that we got it. What it takes to achieve that. This is just repeating what I said. Designing a domain-specific language, if you like, for specifying what it is that we want from our software with a deal of precision. And then specifying what we aim to achieve in detail all of the time. And those are all of the behaviors of the system. Not just the conventional user behaviors that we might think about. We're not talking about sketchy testing of the system, but all of the behaviors of the system. So how fast would we like the results back if performance matters? How secure do we want it to be if we want our system to be secure? Because all of those are contextual. You can't have the AI to infer that, to make it up, because it depends. The real, how secure do you want your system to be? You'd be stupid to apply the level of security to a single user game than you would if you were building a system for a bank, because you'd be over-engineering the game and probably under-engineering the bank. So you need to be specific about what it is that you're trying to achieve in all of the dimensions of architecture and design. So some of those are behaviors of the system that we need to specify too. The second problem, how about that? So how do we confirm that we got what we wanted? In the past, we hoped that our solution solved the problem. Language verified some aspects of this in terms of the syntax that we use, particularly if we use typed languages and stuff like that. But it didn't work to verify functional correctness. If you were a well-behaved test-driven development developer, then testing would fill that gap and would verify that our code did what we wanted it to do in that sense. But otherwise, maybe not. In the future, our executable specifications will work as the verification of our system as well as the specification of what it is that we aim to achieve, I think. This makes the AI, we can do this in human language. This doesn't have to be difficult or hard. The way that I do it is that I teach my AI how to do the kind of BDD style tests that I like to use, and I specify what I want, and my AI fills in the gaps from relatively simple English descriptions of what it is, what the specification of what I want. AI generates solutions that match the specifications. And now we can run those tests against those solutions. We can verify that the AI is doing the right thing by giving test values that it hasn't seen before, so it can't cheat the tests. And get feedback that we actually did get what we wanted, what it takes to achieve that. The programmer invents problem-specific DSL, defines all of the desired behaviors of the system as prompts to the AI in the form of BDD-style specifications, and the AI takes the specifications, builds test infrastructure to make them executable, generates code to fulfill all of the executable specifications, and we've got what we wanted. We've got a precise definition of the behaviors that we want and a verification that we got those behaviors. Regaining the last of the three, regaining incrementalism. So in the past, we would work iteratively in small steps, adding new tests and code. We would gather feedback validated by our deployment pipelines, build systems incrementally, treat each change as an experiment, and value empirical learning. In the future, we're going to work iteratively in small steps, adding new tests and code. The AI will generate the code. Gather feedback to validate every change. Build systems incrementally, many small changes, treat each change as an experiment, and value empirical learning. So it's exactly the same. So the stuff, if you've been practicing continuous delivery, as two of the speakers that I heard speaking today said, at least implicitly, then things become easier. Because that's what we're doing, the same things. We're evaluating stuff as we go, working in small steps, and we're understanding where we are at all times. And so are our AI agents. What does this take to regain the incrementalism in this sense? Well, we version control the specifications because those are now, in effect, our program. We run the tests ourselves in a deployment pipeline. Otherwise, the AI is going to cheat. And we're going to stop the AI gaming the tests by using the sorts of techniques that I mentioned about maybe keeping some tests back and not showing the AI for so it can't cheat them. Most of this that I've described is how acceptance testing with behavior-driven development already works. So this isn't anything necessarily new. If you've been working this way before, this is a really simple step. Here's an example that I've used. I've done this now several times, many times, for building real systems. This is not a real system. This is an example from a training course that I did an exercise with. So here are some the kinds of specifications that I'm talking about. If you think about what I'm trying to describe, we start off with a vague wish of what we want. We get to a slightly more formal version of describing that, which is a user story. And then we come up with some examples that would demonstrate that the feature that the story describes exists. Those are our examples. Those are our executable specifications. That's what these things are on the screen. These are the ones that prompted building a system that actually did this. It actually did flight planning in this way. My conclusions are that natural language alone is not good enough. BDD-style domain-specific languages are the best alternative for prompting effectively and giving us the combination of precise specification of what we want and built-in verification that we got it. Automating testing from a solution is a bit of a joke. It's a niche. It has some utility, but it's a corner case. It doesn't solve the real problem. We should treat skills to analyze and decompose problems as the real core of our discipline. That's the real discipline that we as engineers, technologists bring. It's that way of reasoning about a problem, of decomposing it and thinking about the corner cases, thinking about the kind of the architecture level. One of the ways of thinking about all of this is that effectively what we're doing is we're invoking a fifth generation programming language, a fifth generation programming system. And I think that's where we're at. So we need a different model for the role of AI. AI assistance is rather like the compiler. We're not going to care for very much longer at all, if we do now, about the code that it generates, because we'll verify that we got the results. And as long as we get the results, who cares about the implementation? It's rather like the move from assembly language programming to high-level language programming. I don't know if anybody in the room is old enough to remember that. I don't quite, but I was an assembly language programmer for a while. And for a while, I used to look at what the assembly language was that was generated by my compilers. But I haven't done that for years. And most people have never done that. So why should we care about what the code that was generated was if we can verify that the behaviors that we wanted are the ones that we got? If you'd like to see a demonstration of this in use, there's an open source project called NWave that's worth a look. That applies this thinking and promotes this way of development. Skip. So that's... I'm going to skip over here because I got... where am I? There. That's the end of my talk. Thank you very much.